Okay, good afternoon, everyone. I apologize, first of all, that we weren't able to post the video. I wasn't able to get caught up and post the video on Wednesday, but we'll make it up in today's class and then Monday and then Wednesday. And then if need be, then the plan is to get caught up by Wednesday. Okay, so today, Monday and Wednesday. And then if we are still behind at that point, then I will, post a separate video. But other than that, I don't foresee any issues in getting caught up. Okay. All right, so let's resume our analysis with the design. So we had stopped here. We had looked at the inverting, no, non-inverting, right? Let's see. Inverting amplifier, non-inverting amplifier. Okay. So in the non-inverting amplifier, V out is, sorry, AV is 1 plus RF over RI. We have the gain. We choose a resistor based on that feedback or feedback resistance and the input resistance value, right? Now, we could also have different values of the power supplies. So if we have let's see, whether it's an inverting or a non-inverting amplifier, and we're talking about design, we always have to keep the power supply limits in mind. So this is plus VCC and minus VCC. So these limits always apply. Okay, these limits always apply. If your gain is too large, then you're going to exceed that limit. So many of the homework problems, the first one and the one that's due on Sunday, they refer to, or not refer to, but you have to take into account the values of the power supply that's being applied to our op-amp circuit. Okay. Happened there, 20. Then because amplifier difference. I forget. Okay, for a difference amplifier. Let's say you're designing for a gain of 8. Okay, gain of 8. Now, ideal amplifier, and that means AV is 8, and our supplies plus minus VCC is equal to 8 volts, plus minus 8 volts. Okay, plus minus 8 volts. All right, so difference amplifier, basically as the name suggests, is amplifying the difference between the two input signals, VA and VB, or V1 and V2. Doesn't really matter what you want to use. So if we have this kind of amplifier, this is going to be plus 8 volts. This is going to be minus 8 volts. That's our V out and minus and plus. Okay. So our job is to, of course, determine the value of the resistances. Right, let's call them RA, RB, VA, VB. So our V out, of course, is directly proportional to VB minus VA, right? Difference. VB is applied to the non-inverting, so difference amplifier will always take the difference, non-inverting minus the inverting, okay? And of course, it's not open loop, so feedback resistor. All right, feedback resistor. Now, because the feedback resistor is in there, let's call it RF. Okay, RF. Now, from the previous explanation, if you recall, if you wanted, let's see, where is the difference amplifier? Right there. If you want a specific gain, like we do in our circuit, a gain of 8, then we take these resistors and we take the ratio and make them the same. So on the input side, we have RA here, and the feedback side, we have RF over here. We take the ratio RA to RB, and that ratio must be the same as the ratio of the two resistors on the non-inverting side, which is RC and RD, which are these two right here. Okay. So if we do that, then we can obtain an expression in terms of the feedback resistance and RA. Okay. So if we use the simplified, or if we wish to use the simplified expression is VB minus VA, and the gain can be given by RF or RA, provided we use the circuit this way, right? And then all of these resistors must be the same. So the ratio must be the same. Condition is that the ratio RF over RA is equal to RF over RB. Okay, that means if we simplify this further, we can take RA equals RB and RF, well, RF is the same as the inverting. So all we need to do is to determine a ratio of RF to RA as equal to 8. So again, simplified difference amplifier, where we don't wish to amplify either one of the signals disproportionately. And so we take RA, the ratio of RA and RF to be the same as the ratio of RF and RB. Okay. And so this would be this is the criteria, RF over RA. So theoretically speaking, we could just take 1K and 8K. Obviously, in real life, we would not get an exact 8K resistor. We can have 1K resistors. You can take a bunch of 1K resistors, put them in series. You can take 2 kilo ohm resistors, put them in series, obtain an 8 kilo ohm. Or you can obtain, there are other resistors such as 10K, 1.2, 1.5K, 12K. We can use any combination of those resistors to obtain a ratio of 8. As an example, we can choose RA as 1 kilo ohm and RF as series combination of 8 times RA series combination. Okay. The consistent theme in all of these design problems is we have a standard equation for the gain. Look at our output. Depending on what our output is, we choose a value of one of the resistors and then we calculate the value of the other resistor. So again, this is design at its lowest, most simplistic level. Okay. We're simply taking the gain. We're not accounting for anything else. We simply assume that our op amp is going to operate in its linear region. It's not going to saturate. And because it's operating in its linear region, we simply take a look at the gain equation. Gain equation for all the inverting, non-inverting, summing, and difference amplifiers is straightforward. You simply choose a value for one of the resistors and calculate the other one. And again, in the book, in the assigned reading, I have it. So in the book, when you read through the examples, they use actual practical values of resistors, right? So unless the question states, in general, when we say design, we are referring to actual practical values that are available in real life. But when I'm explaining, I'm not making that as a criteria. Okay, does that make sense to everyone? Right? When you're actually designing, if you want to build this in the lab, it will work, but then you're constrained by taking actual values that are available to us. Okay, meaning there is no such resistor as 2.6K. But if you're doing a theoretical calculation or a theoretical design, 2.6K, you end up with 2.6K, that's fine. I'll allow it. Okay. And real life, obviously, you can make up a 2.6K by connecting resistors in series and parallel. And people often do that, right? Trying to fit the design into a particular given value, it's easier to just take a bunch of components and create your own. All right. So one final topic is ideal op-amp versus a real-life realistic model. So properties of ideal op-amp were that it has infinite input impedance or input resistance, 0 ohm output resistance, and infinite open loop gain, right? A realistic op-amp, that's not the case. We have a finite value of resistance that's connected between the inverting and non-inverting terminal. We also have a certain value of resistance for the output. And more importantly, at the output, we can model within the linear range of operation, not saturation, linear range of operation, that the output is a multiple of the input, right? We say V out is directly proportional to V in. It's a multiple of V in. So it's the output voltage is dependent on the input. So it can function as a dependent voltage source. It is providing a voltage at the output, so it's a voltage source, but it depends on some other quantity in some other part of the circuit. In this case, it depends on the input voltage. If you want a complete model, we would describe it as a difference of the input voltage at the inverting and the non-inverting terminals. And so we can describe it as VO is directly proportional to VP minus VN, the non-inverting minus the inverting input terminal voltage. And the dependency, VA, more appropriately correct would be AV, the voltage gain. Okay. So in the book, there is an analysis based on these conditions. But again, in class, it's not something we'll go into. All right, so this again, if you remember, is a let's write dependent voltage source, right? Output is a voltage that is dependent on the input. The open loop gain is also finite, meaning it's not infinite, and there is a all right, let's take a pause while you write it down. Okay. Are you all familiar with frequency? Frequency in hertz, like we talked about AC cycles, and the number of cycles in 1 second is frequency. So frequencies are very important quantity in electrical engineering. We use them all around us, right? Every signal that we deal with has a frequency. Power outlets have the frequency of 60 hertz. Our wireless routers have an operating frequency of 2.4 and 5 gigahertz. AM radio stations, AM stands for amplitude modulation, which is you're modulating the amplitude or the y-axis quantity. FM is frequency modulation. You're changing the frequency of the signal. Then there is, well, you'll learn about all of those in EE 314 communication systems. Anyway, the point is there are frequencies all around us. So with regards to the op-amp, with regards to any system, we are applying a wide range of frequency signals, right? When you apply a wide range of frequency signals, the device or the circuit that we have created is only going to respond to a certain band of these frequencies. For an op-amp, if you plot the gain versus frequency, or gain as a function of frequency, the frequency is on the x-axis, this is 0, this is increasing, right? This is increasing. Actually, I don't need to draw the arrow again. And let's say this is the gain. For an ideal op-amp, obviously, the gain is going to remain infinite and it's going to remain a flat line. But for a real life op-amp, it's going to start dropping off. This gain is probably, I don't know, has a value of 100,000 approximately. Even the smallest or the most common op-amps have a gain of about 100,000. But then beyond a certain frequency, it's going to start dropping off. And if you, I don't know, in the lab, do y'all do an experiment with an op-amp, like an inverting, non-inverting amplifier at all? Do y'all have experimented with op-amps? Yes, no, a little bit. Have you created an amplifier with the op-amp? Okay. So, and you could try this very easily. So you create the amplifier and you applied an input frequency signal. What was the input frequency that you applied? Does anyone remember? A few kilohertz, maybe? Anyway, whatever input frequency you applied, the op-amp, it amplified the signal. But then if you keep the input voltage the same and you increase the input frequency and you keep an eye on the output voltage, you will see that the output voltage, while it was quite large, when the frequency increases, the output's going to start getting smaller and smaller. So you go up into the megahertz range, which is 10⁶, not that high frequency actually, considering everything, all other frequencies that we use. So megahertz range, start seeing the op-amp gain start to diminish. It's an easy experiment, an easy experiment to verify. Okay, so next time you're in there, if you have some time, you build an op-amp circuit. All you got to do is just crank up the frequency, and you'll see it start getting small. And that's what this represents. Okay. Okay, so say we're at the end of chapter 5, and then we come to one of the other most important chapters, which is chapter 4 in the book, which is the other techniques of circuit analysis. Okay. Oh, should have started here. Okay. I don't know why I did this. All right. So our book calls chapter 4 as techniques of circuit analysis. And here is where we learn about node voltage, mesh current, superposition, and then Thevenin-Norton theorems. If you all recall at the beginning of the quarter, I said the entire class is important because everything that we learn here, you're going to use it again and again and again and again later on for the rest of your career. And so every single time, let's say when you get to 211, 212, 306, 307, 308, there'll be circuits and you'll be quickly asked to like analyze it and it'll say, okay, yeah, we're going to apply KVL here and we're going to generate an equation, or we're going to create a Thevenin equivalent and we're going to generate an equation. So this is what we're going to do in this chapter, right? But the only three equations or laws we need are, what do we need? That's it. Those are the only three ones we need. Everything else is based on these three, right? Ohm's law, KCL, KVL. And that's why we had individual homework for all of those, all of those topics. So from Ohm's law, we already saw two other shortcut techniques, which were voltage division and current division. We also determined how we could add up resistors in series and resistors in parallel, right? All of those were based on Ohm's law and then KCL and KVL. Now we are going to learn two other techniques called node voltage analysis and mesh current analysis. And those two techniques are a combination of Ohm's law and KCL and Ohm's law and KVL. Okay. So I'm going to just, actually, I've never done this, but today I'm going to do this. On the first slide, I typically don't have anything introduced in the chapter, but today I'm going to do something and I'm going to explain. So let's start at the end of the chapter, okay? There is something known as Thevenin equivalent circuit and Norton equivalent circuit. These are not techniques, and you don't have to write this down because we're again going to look at each of these topics in detail anyway. So Thevenin and Norton are not techniques per se. They were theorems. They were postulated by engineers in the past. And Thevenin and Norton both are about more than 100 years old now. Okay, very, very powerful techniques. So again, they are not analysis techniques per se. They're equivalent circuits. They are theorems that we apply. Okay. But to determine the Thevenin and Norton equivalent circuits, we can use any techniques we want. Two of the primary techniques we use is node voltage analysis, which I like to call NVA. Again, we'll study about those. And then, or we have MCA, just mesh current analysis. There is also something known as superposition, SP. Okay. NVA, MCA, SP, all of these again are different kinds of techniques because if you try to solve the circuit with just Ohm's law or KCL or KVL, it can get too laborious. It'll take a very long amount of time to solve it, so it's highly inefficient. Plus, we may not even be able to derive enough equations to solve them, okay? So we derive NVA, MC, and SP, and these in turn are derived from Ohm's law. Well, this is not quite like that. Should be like this. KVL and KCL. Okay, so we learned about KVL, KCL, and Ohm's law in chapters 1, 2 in the preceding chapters. I'm going to combine them, learn about NVA, node voltage analysis, mesh current analysis, superposition, and from there we apply those techniques to determine the Thevenin and Norton circuits. And I cannot emphasize strongly enough how important these are. Okay. So again, you practice. I'll set up a lot of homework assignments, problems, practice problems, but I need each and every student to get really comfortable with determining the Thevenin circuits and applying node voltage and mesh current analysis. Okay. And then I'm there to help you with every step of the way. All right. So enough with the foreboarding, and let's jump into the topics. So we talked about node voltage, or it's not talked about. I mentioned node voltage and mesh current. So let's talk about what nodes and meshes loops mean, right? Node is a junction point. A node is a junction point in a circuit. It's a connection point, it's a junction point in a circuit where two or more elements are connected together. And that's it. It's a junction point in a circuit. So if you have a circuit, that's a node. And that's a node. Anywhere where you have two or more components connected together is a node. A conductor or wire is something that connects two nodes together. Okay. If you see connections like two nodes, but there's no component between those nodes, then they're the exact same node. Okay. So and this is sometimes a hard concept to grasp until and unless we get familiar with it. In theoretical circuit analysis, a node can be a dot, can be like a small dash, can be like a small wire extension, could be like a really long wire. They're all the same exact nodes. All circuit analysis that we perform in class is all theoretical. Theoretical means it's all ideal components. Ideal means if it's a conductor or a wire, it has 0 ohm resistance. A dot is the same as a small dash, is the same as a small line, is the same as a long line. Okay, but it means it's the exact same node. Anything that's connected between two nodes, if there's a component between two nodes, that means they are two separate nodes. But if there's a wire between two or more nodes, then they are all the exact same node, electrically speaking. Okay, so identifying nodes is the most important. A real life example would be if you take your power outlet, if you take the power outlets that are across, across the walls in this room, and you plug in an extension cable. If you plug in a 6-foot extension cable, you'd expect to get power at the end of the 6 feet. If you plug in a 50-foot extension cable, you'd still expect electrical power at 50 feet. If you plug in a 100-foot extension cable, you would still expect electrical power at 100 feet. So it's the exact same node, right? Does that make sense? Now, however, if you plug in like a 1,000-foot long cable, or maybe even longer than that, thousands of feet, now that cable would have some resistance. Does that make sense? So instead of 120 volts, you might obtain like perhaps 100 volts. There is a voltage drop across thousands of feet. Okay. Theoretical analysis doesn't really matter. You could have a 10,000 feet long cable. I could say this is like 10,000 feet long. It has 0 ohm resistance. Same equivalent node. All right. So coming back to our point here. So a node is any junction point or connection point in a circuit where two or more components are connected. If two nodes are connected by a wire, it's the exact same electrical node. There's a subset of a node. If there are 3 or more components connected to a node, we refer to it as an essential node. It doesn't really, I mean, it's there, it's a technical definition, but it doesn't affect our understanding of circuit analysis in any way. Okay. I've rarely ever heard or read anybody refer to something as an essential node. Okay, essential node would be something like if you have like a VCC power rail, everything's connected to the positive rail. If you have a ground line connection coming in, that's an essential node. Or you could have like 3, 4, 5 components connected at one single node. That's not a power rail. That would also be an essential node. But essentially, an essential node is a subset of a node. I don't consider it to be that important. This is more important. A loop and a mesh. A loop is something that we're familiar with because we apply KVL, right? So a loop is a closed pathway. If you start at a node and you go around the circuit, you come back to that same node, going around the circuit, you come back to that same node without going back on any one of those nodes. That is known as one loop. Again, a loop is a path where you start at a node and you end up at the exact same node. So it's a closed pathway that allows current to flow through. And that is known as a node. More importantly, any of the other nodes are not repeated more than once, except for the starting and ending node. Okay, because it's a closed pathway, right? Whether it's a rectangle or ellipsoid or however it's connected or shown, is a closed pathway. Starting node and ending node are the only ones. So the starting ending node is the only one that is repeated twice. All other nodes in that loop are just considered or rounded once. Okay, so that's an electrical loop. And then a mesh is a subset of a loop, and it does not contain any other loop inside it. Okay, a mesh is a subset of a loop that does not contain any other loop inside it. And I'll explain what it means on the next page. All right, so here we have a circuit diagram. Let's walk with me. How many nodes do we see here? 1, 2, 3, 4, 5. I'm sorry, how many nodes? 6, 7, 8, 9, and 10. How many do you see? Speak up. There's no penalty on speaking up. Even if you're wrong, I would actually hope that students are wrong because we learn from our mistakes. Does anyone see more than 10? Okay, how many do we have on the left side of the room? 10. She disagrees. 9. Okay. How many in the middle of the room? Okay. You said 6. You said 5. Okay. At the end of back of the room. How many? 10. 7. 10. All right, let's see. All right, basic definition. Where two or more components meet, right? So circuit is saying that all these black dots is a node. But the second part of the definition is if two nodes are connected with a wire, they are the exact same node. So on the far left, we have all of these connected by the same wire. So they are the exact same node. And then 2 is a valid node. 3 and 7 are the same nodes. So I would say all of these are connected by the same wire. So let's call this 3. And then in the middle, this is all connected by wire. So this is all 2. And then 3, and this would be 4. And then this would be 5. Ding, ding, ding. You win the prize, but I don't have any prize. You want the satisfaction of being right. Anyway, so the first definition of the node, or the first line of the definition would be 2 or more connections. And then if there are only wires between those connections, then it's the exact same electrical node. And the reason I'm harping on this and making it slow is because in node voltage analysis, so first thing we need to do is identify the nodes, and it's tricky. It's very tricky. So every student takes their own time. For me, it took a long time when I was a student. This is like more than 30, 35 years ago. It took me a long time to get my head wrapped around how to identify circuit element in series, what is a node, what's in parallel, what's not in parallel. So I think every student works at their own pace. For me, it took a while. Some grasp it quicker than others. But whatever advice is practice as much as you can looking at different circuits. Okay. So we have 5 nodes in the circuit. Okay, 5 nodes in the circuit. Then what I'm going to do is I'm going to ask you to identify how many loops do we see in the circuit. So I'm going to wipe this out. Okay. That's 1, 2, 3, 4, 5. Okay, how many loops do we see in the circuit? Actually, you know what? Instead of a loop, let's first identify the mesh. A mesh is a simple loop. Okay. Excuse me. You start at one point, you end up at the same point, and it does not contain any other loop inside. So I start at this point and I go around this. This is mesh 1. I start at this point and I go around here. That's mesh 2. Start at the bottom in the middle. I go around. That's mesh 3. That's mesh 4. Mesh 5. Mesh 6. And mesh 7. Each of these meshes is a closed loop, but it does not have any other loop inside it. So meshes are very straightforward to identify. Does that make sense to everyone? So there are 7 meshes, 5 nodes and 7 meshes. And this is going to be important later on. Okay. Does everybody see this? Any questions? Okay. Now, as far as loops go, we have more than 7 loops. Because loops are basically you start at a node, you go around the pathway, and you come back to the exact same node, taking any path you want without going back on that same node. Okay. So for a loop, let's start with the outer loop first. So any circuit you have, you can start with the outer loop. So you have one big outer loop. If I start at the outer loop, that's the big outer loop, right? Let's say that's loop 1. Now here's the difference between a loop and a mesh. We counted 7 meshes, right? 7 meshes. So 7 meshes, there are 7 loops, right? Every mesh is a loop, but every loop is not a mesh. So meshes are easy to identify. We counted 7 meshes in there. Now we have one big outer loop. This outer loop is not a mesh because it contains other meshes inside it. And that's the meaning of that statement. A mesh is a simple loop that does not contain any other loop inside it. If you look at this outer loop, you have 7 different meshes or 7 different loops inside it. So this big loop is not a mesh. Does that make sense to everyone? Right? Have you all studied this before, by the way? Loops and meshes? Okay. All right, so we have one big outer loop. So I'm going to mark this. Then you can take this one, that's 2, right? So let me do this. Actually, so 1, right? That's 1. That's 2. And then that's 3. This circuit has many loops. I don't think I'm going to get the right answer. It's 3. And then where was I? That's 4. That's 5, 6, 7, 8. So this would be 8. And this would be 9, 10, and then 11, 12, 13. So there's too many loops in there to count. But hopefully you get the idea of what I'm trying to say. Does that make sense to everyone? A loop is any closed pathway you can take. And the beauty of law of conservation of energy is that KVL applies to each and every loop. Doesn't matter what values the voltages are, what values of the dependent sources, anything in there. The law of conservation of energy still applies. And so KVL applies to every single loop. This is a fundamental fact that my head can never understand. I don't know. My brain just cannot grasp that concept. I know what law of conservation of energy is. I know what KVL is. I know how it works, how it's applied, and I just still I can appreciate the beauty of that of KVL, but it's hard for me to explain how it actually worked like that. I don't know if that makes sense. But there are not infinite, but there are like multiple pathways, there are multiple loops, and KVL applies to all of them. Okay. So that's nodes, meshes, and loops. All right. Then before we get into node voltages and mesh current analysis, let's talk about how we can express each of those. Oh, any questions about anything you've covered so far? Okay. All right. Voltages are always measured with a reference point, right? You'll remember single subscript notations. If it's VA, we mean voltage measured at A with my reference at ground. Okay, VA means VA 0. Now that 0 doesn't necessarily have to be ground. Okay, it could be a different reference point in the circuit. I believe I did an example of like I did a one-dimensional diagram of like points in a circuit with like different voltage levels. Do you all remember that? Points A, B, C, D, E, F, G. Let me see if I can find it. I can't remember where it was. Not here. The chapter 2. Oh yeah, this one, this example. We had 6 points in a circuit, A, B, C, D, E, F. A was at actual ground level, so its potential, electric potential of A was 0 volts. E and F were below 0 volts, right? So 1 volt and 2 volts below 0. So if A was my reference, then VE and VF would be -1 and -2 volts, right? It's below. So if A is my reference, B, C, and D are 5, 4, and 2 volts, +5, +4, +2 volts. If B is my reference, B at the top is my reference, then all other voltages, measurement points are below B. So all of them are negative. So VA would be -5 volts, VC would be -1 volt, VB or VD would be -3 volts. So it depends on what your reference point is. So voltage is simply the difference in potential between any 2 points, right? There's difference in potential between any 2 points. Doesn't matter what your reference is. Actual ground does not have to be your reference. And this is going to be important in node voltage analysis. That's why I'm going back again and doing this. So again, please review this again and let me know if something doesn't make sense, all right? You need to be familiar with that. But we talked about nodes. So now we're talking about node voltages. When we say node voltages, we'll refer to single subscript notation. So VA, VB, VC, VD, and so on and so forth. The reference point is implied. Okay, the reference point is implied. So this, actually, let me not say it's just reference. And this reference point is implied. It's not stated. Okay, so VA means voltage measured at A with the reference point of the circuit. And here's the important thing. The reference point does not necessarily have to be ground. It could be any point in the circuit. Okay, the reference point can be any node in the circuit. Okay, in this example here, this is shown as the reference point A. Okay, A is shown as the reference point, and it shows that there's a ground connection in there. Sometimes you will read books or you will read some papers, or maybe some professor is talking about a circuit. It does not mean that it is ground necessarily. It could be that it's just the reference point for the circuit. That's all. Doesn't mean it's physically connected to ground. Okay. So this ground symbol could mean it's connected to actual ground, but more importantly, it simply means it's the reference point for the entire circuit. That's all it means. If I was analyzing this circuit, depending on the circuit configuration, I could choose B, C, or D as my reference point, and then my voltage would change. The important thing is, whatever is your reference point, the value of the voltage at the reference point is equal to 0. Okay, it's equal to 0. So voltage at reference, Vref, is 0 volts. So in node voltage analysis, the first thing we do, or first step we take, is to identify all the nodes in the circuit, and you pick a reference node. And once you choose a reference node, you already have an answer for the voltage at the reference node because it's 0. You're measuring voltage at the reference point with reference to that same point. No difference in that potential, so it's 0. That's the logic. Here, 4 o'clock. Okay, let's stop right here. I wanted to cover a couple more slides, but I think I went a little bit too slow. All right, so we'll have a quiz on Monday. We haven't. It'll mostly be like short answer questions now, like op amp homework a little bit. Um, and I might, there are students, a couple of students had asked for an extension, so I might just do that too. I might extend the homework. How are y'all doing on the homework, by the way? I know one or two students had some questions. Are y'all done with the homework? Working on it, right? So I might extend it by like a day or two, maybe till Tuesday perhaps instead of Sunday. That'll give you some time to ask questions. And so the quiz will deal with the op amp. So it'll be certain parts of the homework, but it won't be too. I don't want to promise anything, but I'm going to say it won't be too difficult, at least from my point of view. Just enough time for students to study. All right, so we'll end class here today, and we'll pick up here on Monday. If you have any questions, feel free. Please send me an email or reach out to me. I'm happy to meet over Zoom. I'll be available all day Saturday and Sunday. Today's the banquet. So, how many of you are going, by the way? Anybody going? Nobody's going? Oh, man. Anyway, this is my first year, so. All right. See y'all next week. Can you, which one? Yeah. Can you send me an email about